Hello again, everybody. Welcome to another video lesson. Today we're going over variation functions. We're going to recognize and solve direct, joint, inverse, and combined variation problems. Okay, these are very specific type of problems here, these direct variation problems. So let's hop right into our concepts. Okay, there are these four types of variation functions that we're going to look at today. We have direct variation, joint variation, inverse variation, and combined variation. Now, all of these have at most, what we're going to look at in this chapter or in this lesson, they have at most three variables and then one constant. Okay, you see down here k is going to be a non-zero constant of variation is what we call k. That is a non-zero constant of variation. So one thing that we're going to need to take away from this slide especially is when you identify these sort of statements here in, say, a word problem, we need to understand how to translate that to an equation. Okay, so if you see y varies directly as x, y varies directly as x, what that means is y, this variable y, changes directly as x changes. And it changes along with this constant, or it changes by a ratio of this constant of variation. Okay, so our constant stays the same, and then say as one variable changes, our other one changes as well. So this direct variation is very similar to just a linear equation, right? Y equals mx plus b. However, in this case, we have no plus b, right? It's just y equals kx. K is kind of like our slope if we were to think of this graphically for a direct variation. Now, joint variation is when we bring in two other variables. Okay, so we kind of have this third variable, in this case z. So if you see y varies jointly as x and z, that means as x and z change, y is going to be changing by this constant of k. All right? So as now two variables change, now my final y that we're looking at is changing by this constant k. So over here with direct variation, it's one variable. Now with joint variation, it is two. And also we have our inverse variation. Inverse variation is going to be if we have our variable x here, if that is changing, and that is in the denominator of some ratio between k and x, all right? So if you have a ratio of k to x, and that is equal to y, you might see that as y varies inversely as x. Okay, so as x is doing something, y is going to be changing. So if k was 1, and y was getting larger and larger and larger, then you could see that if x is getting larger and larger and larger, then since that is in the denominator of this fraction here, y would actually be getting smaller and smaller and smaller. So y would be going down as x went up. So that's why we say an inverse variation, because they're going opposite directions here. Over here, as x goes up, y also goes up, right? If we plug in 1, we're just going to get whatever value is for k, for y. But if I plug in 10,000, so x goes way up, then y is going to go way up as well. Okay, and then combined variation, there isn't a specific equation for combined variation, but y is going to vary directly and or inversely with some other variables, okay? So it could be y varies directly as x and inversely as z. Okay, so we have a combined relationship between y and the other variables of x and z. All right, so make sure you take down these equations and make sure you take down these phrases to be looking for in all of our word problems. And let's hop into some examples. Okay, first one is going to be direct variation. Y varies directly as x, and y equals negative 15 when x equals 5. Find y when x equals 3. So since we see that y varies directly, we're going to use our direct variation equation that says y equals kx. Again, this is just sort of like a linear equation, right? So if I've got y1 equals kx1, then again, if I were to plug in different values for y2 and x2, my k value is a constant. So that is going to stay the same, all right? So if I were to take this information that we're given, and we know that y is equal to negative 15 when x equals 5, okay, then I could say y1 is negative 15, x is equal to 5, or x1 is equal to 5, and I can plug those right in. We're going to do that in order to solve for k. Okay, so I divide by 5 on each side, and I get k is equal to negative 3. Now, why are we solving for k? Well, because I now have this other situation that we're going to solve for, because we're asked to find y, right? We don't know what y is, when when x is equal to 3. We're finding y when x is equal to 3. So my y2 I don't know, that's my question mark, that's what we're solving for. x2 is equal to 3, so I can just plug in negative 3 for k, and I can plug in positive 3 for my x, because that's what we get from the problem statement, and we get that y2 is equal to negative 9. All right, so that is direct variation. Let's take a look at our joint variation. Suppose r varies jointly as v and t. So again, this does not always have to be x, y, and z. Okay, it can be whatever variables are in this relationship together. All right, so find r when v is equal to 2 and t equals 8, if r equals 70 when v equals 10 and t equals 4. So we're going to use our joint variation equation here because we have multiple variables that are affecting our final y value. Okay, but in this instance, we have an r that's equal to kvt. Okay, since r varies jointly, and that's going to be what's over here on this side of our equation on its own to start with, okay? So I've got R1 is equal to K V1T1, and then we're going to use this second situation as well to actually solve. But first, we need to find our K value. So we know that R is 70 when V is 10 and T is 4, so we just plug those right on in, and we can solve for K. K is going to be 7 over 4. Now, what are we looking for? We're asked to find R when we're given the given V and T values, but we don't know what R is. But we can just go ahead and plug in what we found for K, plug in our V and T values, our other V and T values, and we can go ahead and solve for R, and that's going to simplify to 28. All right, let's take a look at our inverse variation. So if X varies inversely as y, and x equals 24 when y equals 4, find x when y equals 12. So this is our inverse variation equations. We can look at this in two separate ways, right? I can say y equals k over x, or I can say k is equal to x times y. Okay, so if you have a product that equals my constant k, a product here that equals this constant k, then you are dealing with inverse variation. All right, so I'll have k is equal to x1, y1, and we're given, we're given 24 and 4. So we can plug that right in and find a k value of 96. And we'll take a look at our second situation, k equals x2, y2. And we can plug in our value for k that we know is 96, we just found. However, we also know this value for y, right? Because that y2 we know is going to be 12. We can divide by 12 on each side and get an x value of 8. Okay, now let's take a look at our combined variation. Now, one note here. So we got p that's varying directly as r, and p varies inversely as t. So we need to find t when r is 10 and p is negative 5, if t equals 20 when p equals 4 and r equals 2. So our note here that we need to think about, if we have quantities that vary directly, okay, very directly, then those are going to appear in the numerator, all right? And if we have any quantities that vary inversely, those are going to appear in my denominator. Okay, so we can have values like p's and t's and r's that appear some of them in the numerator and some of them in the denominator. That's why it's called combined variation, because it's both directly and inversely varying our p values, okay? So p is going to be k r1, because again, r1, p varies directly as r, okay? So it varies directly, so it appears in my numerator. And p varies inversely as t, so that's going to appear in my denominator now, okay? So that's how we can come up with this equation here. And all we need to do to solve for k is plug everything in. Okay, so I'll have 2k over 20, so it's going to simplify to k over 10. Multiply both sides by 10, and we get a k value of 40. Now let's take a look at our second situation here. This again is the same starting equation that we're going to work with, but we're asked to find t, right? So since we're asked to find t, we need to go ahead and multiply both sides by t2, and we'll divide both sides by p2 as well. And let's see, we'll end up with a simplified equation once we cancel some stuff out or simplify some of those ratios. We'll have t is equal to k r over p. So again, we just plug in everything that we know based off of our when r is equal to 10 and p is equal to -5. And we find a t value of -80. All right, last example, we're going to apply all of this information here, or all of these concepts, in a real world example. So if the apparent length of an object is inversely proportional to one's distance from the object, Earth is about 93 million miles away from the sun, and Venus is about 67 million miles away from the sun. How much larger would the diameter of the sun appear on Venus than on Earth? Okay, so we have an inverse variation here, okay? And so we're going to be working with y equals k over x. Or we can take a look at k equals xy, which is what we're going to start off with here. Now we need to define our variables. What is x and what is y? So we're going to say that the apparent length of an object is going to be y, and then the distance between the objects is going to be, in this case, between the planets from the sun, is going to be our x value, okay? And since k is the same in both of these equations, k does not change, so k equals k, which means x1, y1 is going to equal x2, y2, right? So now we need to just define which of these situations is for Earth and which one is for Venus. So we'll say the first one's for Earth, the second one is for Venus. And what we're looking for, how much larger would the diameter of the sun appear? So what we're looking for is this ratio of the apparent length at Venus to the apparent length on Earth, because again, y is my apparent length of the object. So in order to do that, we would divide both sides by x2. Those will cancel out. We'll also divide both sides by y1. Those guys will cancel out, and we are left with this exact ratio here, y2 over y1 is equal to x1 over x2. So x1 is going to be the distance from the sun to Earth, okay? And then x2 will be the distance from Venus to the sun. And so that's going to be 93 million miles over 67 million miles. And we get about 1.39 times larger on Venus is how much larger the diameter of the sun appears. All right. So that's all I have for you guys for this lesson. Good luck with your practice.